Welcome to Intro2Astro 2024.
Back everyone to Intro2Astro 2024. This is our third session. Today we'll cover Matplotlib, which is essentially plotting in Python. We'll show you some of the exoplanet detection method, which is a hot topic right now in astrophysics. And finally, we'll finish off by introducing the NASA Exoplanet Archive, which is an online database that contains various information about exoplanetary systems as well as the general population. Okay, before we start, is there any questions? Feel free to type in the chat or just unmute yourself. Or maybe suggestions for the workshop in general. Any feedback is appreciated. All right, it looks like there's no question. As always, you can type your question in Discord, and we'll do our best to answer them. Okay, let's get started. Josh, do you want to begin and maybe introduce yourself a bit?
Sure. So my name is Joshua Lieberman. I am a soon-to-be second-year PhD student at the University of Arizona, and my research is in extreme adaptive optics. So Maria is going to tell you more about adaptive optics a bit later in the course. And then also I work on direct imaging, which is one of the detection methods that we'll cover, where you're basically trying to take a picture of a planet and remove the starlight from your picture. Yeah, so I can share my screen now.
Yes.
Yeah, so this.
Go ahead.
Oh, as Faye mentioned, this is an introduction to Matplotlib. So just briefly, what is Matplotlib? It's a plotting library for Python, but within all fields. So here are a few example plots. Is pretty straightforward. I think that participating in the AstroPy tutorials, then you probably already have it installed. And then as far as importing the plotting functionality, you will see a lot throughout your programming journey. Basically, here where is the library Matplotlib, and then from that we're going to import this plotting module. And then this last part is what's known as an alias. So you don't technically need to import PyPlot as PLT, but it's standard convention in programming to do so. So now let's get into what this library looks like. So as I mentioned before, you can create many visualizations in Python with Matplotlib. So here we're importing PyPlot and NumPy, and we're also importing this. We're going to install and import this library called SciencePlot. And what these give you are what are called style files in Matplotlib, which is basically a file that outlines some formatting parameters. So because the default Matplotlib plots aren't super interesting or like publication ready on their own. So using these style files, you can basically format your plots however you would like. And you can also create your own. So getting into the actual plotting, let's say we want to plot the function y equals x squared. So we first need our data points. So here, as discussed in the previous lecture, we're going to use linspace to generate 5 numbers between 0 and 10. And this is going to be our x variable. And then for our y variable, it's going to be x squared. And so plotting this, we're basically going to see a line that isn't super smooth, and that's because we only have 5 data points. And also something worth noting, if you're using a Jupyter notebook, you don't need this plt.show, but it's often good practice to include it, because if you're using a Python script, this line is what will display the actual plot for you. So because I mentioned this line isn't super smooth, we can increase the number of data points. So when we do that, we have a much smoother curve, as you see here. But now we can change the plotting style a bit, customize a bit. So here we're specifying the color of the line, which is red, and then we're also using this argument ls each, and ls means line style. So there are a few different options you can include for line style when you're customizing your plot, and these values are shown here. Additionally, you can see points along your line, and so we do that using this argument here, O dash dash, and you'll see that this tells us that we're plotting our points here, and then we also have a dashed line on top of that. And then we have these additional arguments, LW, which means line width, and then marker size, so where we set the size of our points on a plot. But there's also an equivalent syntax you can use, which might be easier to remember when starting out, where it's just the same arguments as above, but spelled out. So instead of using ls, you can also say line style, and separately you can define the marker, and as well as the other parameters. In this way, it just kind of helps to self-document your code. And as you continue as a programmer and a researcher, you'll learn that documenting code is very important so that other people can follow along with what you're doing. So additionally, we can change the figure size for our plots, and we do that here with plt.figure, and then setting the figure size within this function. So when we have more than one plot, we also want to add a legend. So here we're plotting, we have our one x variable, our linspace, and then we have we're plotting 2 functions. So one of our functions will be for sine x, and then the other one will be for cosine x. So we can plot them on top of each other by calling plt.plot twice. And then just this syntax within the label. So this label allows you to create the legend. And then the syntax inside here with the $signs is LaTeX. And you'll learn more about that later in the course. It's basically for formatting equations and documents. And then here you can also specify your location of the legend, as well as your font size and columns within the legend. So as you can see, the position of your legend, there are multiple options you can choose from. And so it's good to be able to position the legend where you want so that it's not overlapping with the data that you want to show. So here's another example where we're plotting 3 functions on top of one another, cosine x squared, sine 6x, and then we're also plotting additional lines here. So you can also save your figure as a PDF as shown here. And so the plt.savefig is of course very useful for keeping track of your plots. But additionally, you can create scatter plots within Matplotlib. So to do that, we're going to use the function plt.scatter. So what you see here is that it's plotting just the data points with no line in between them. And again, we can create a legend for this data. Additionally, you can plot histograms in Matplotlib. And so here what we're doing is we're generating a sample of 1,000 values from a normal distribution with a mean of 0.4 and a standard deviation of 0.2. And what that looks like here is we define our figure, and then we use the function plt.hist. And you'll notice there's this additional argument called bins. And that basically tells you like how you want to kind of separate your data. So you see here, when I don't specify bins, we have these larger kind of blocks, whereas you can increase the density or like the resolution of your plot by increasing the number of bins. Additionally, we can choose to draw only the boundary as shown here. And another really powerful feature of Matplotlib is the ability to create subfigures. So this is what you'll be using pretty often as you progress as a researcher. And that's because this method allows you to create multiple diagrams in the same window. And it's very versatile when you want to customize your plots. So here, where this function, we have two variables from this function. Figure is like the canvas. So the basically controls the size of our overall figure. And then axes has to do with kind of everything that we're plotting. And so you can see that laid out here. And then the other thing worth noting is this is also a really good argument to include in your code, tight layout. And it basically reduces extra white space from your figure, which is very helpful when you're saving out your figures. So additionally, you can create error bars in your plots. And so you do that using plt.errorbar, and you include your X and Y arguments. And then you also specify the amount of error using this Y error parameter. You could, and so here it shows various methods in which you can do that, where you can create both upper and lower limits for your error, or just plot one or the other. So additionally, of course, Matplotlib is very applicable within astronomy. So here we're going to open up a FITS file, which contains a spectrum. So you can see here that here we're plotting wavelength against flux, and you can overplot horizontal line or vertical lines on your plot using Matplotlib. And this is very useful for examining a specific wavelength in your spectrum. But additionally, we can also plot HR diagrams. So here we're calling in data from the Gaia database, which is a satellite which contains, which gives us a lot of really useful data on stars. So what that looks like here, here you can see our two HR diagrams, and we're using this hexbin argument, which is particularly useful when you have a lot of data, because it just, it basically makes your plots look a lot neater. Additionally, we can use FITS files. We can open up images and look at those as well. And so this is what I do quite often in my research. And so you do that using plt.imshow. And here where I'm adding in this extra argument origin equals lower, which I do all the time when plotting images. And it's because when you specify this argument, it'll set the y-axis to start at 0. Otherwise, your image will appear flipped. So you can see here, we've changed the color map, and we've also included a color bar. So below also are some exercises, basically, that you'll be doing for your assignments. And then additionally, we have more resources at the bottom. And I just want to take a minute to briefly go over some of these resources, because it can be, sometimes it can be very overwhelming to be presented with a whole PDF, like a whole book basically on programming. And it can be hard to know where to start. But within research, learning how to look up documentation to find the specific code that you want is a skill in and of itself, similar to learning how to read papers. So how I often utilize these resources is when I'm trying to figure out how to use a new function, say in Matplotlib, is I'll do it kind of on an as needed basis. So let's say, for example, I want to create another image within this one that appears zoomed in. So I might go to this link here and I can just search zoom. And then I found the code that I want, which will basically help me to execute this plot. So this might seem straightforward, but it's a very useful skill basically as you continue to progress in your journey as a researcher, to basically call upon these resources as needed. So yeah, that's everything.
All right, thank you so much, Joshua. It was very informative. Yeah. I learned something new too. All right, maybe this is a good point to pause for questions.
Sure.
Raise your hand if you have a question, or you can simply type in the chat.
Yes. So yeah, you're correct in noticing that I used SQL here. So basically, there are multiple methods of querying data, and this is one way you can get data from this database. And SQL stands for Signal Querying Language. So this is another programming language, and basically what it's saying within this command is we're selecting multiple variables from this database, and then we're including this parameter where parallax is greater than 50. So for Gaia, it's helpful to use this kind of syntax because of just how much data the Gaia database contains. And so this allows you to basically acquire your data more easily than just trying to search, say, using a search bar. Yeah, I don't know if that helps.
Yeah,
but,
SQL is now covered in the course. It's a bit more advanced for what, but there's plenty of information online if you want to learn about it. All right, any other questions?
Oh, is that? Oh, sorry, what was that question that's just posted in the chat?
Yeah, how do you know of the right parameters to select when selecting data?
Well, that will depend on your research case, I think. So I don't know if you have more to add to that.
I think what Equity meant is, how do you know the column name? I guess this is by reading the documentation of the data release. Usually the science team, they will decide on a standardized name for the various parameter. That's what you see in cell 32. So you have to look this up in advance.
Yeah.
So Alif has a question. I don't know the subject, but it's getting better with the narrations. Thank you. Okay, of course. Yeah, comments are also welcome. All right, let's move on. Thank you again, Josh. Rena, you ready?
Okay. Where am I sharing my screen? You guys see my screen?
Yeah. Go ahead.
Okay, so we're talking about exoplanet detection methods. Have you guys talked about exoplanet detection at all yet?
Not at all. So
Not
maybe
at all.
start from the very scratch and maybe introduce yourself a bit.
All right. Well, to introduce myself, Yeah, to introduce myself, my name is Rena Lee. I am just advanced to candidacy graduate student here in Hawaii. I work with Faye actually. I study ultra short period exoplanets, so planets that are on really, really short orbits, less than a day, really close to their host stars, to study planet formation. So I do a lot of planet detecting. I'll go over how we do that. So to get into it, I just like this kind of diagram that came in the slide deck that I chose. We have a lot of different types of planets in our own solar system that you guys might be familiar with. The rocky planets in the inner solar system, the gas giants and the ice giants further out. We find a lot of systems like this, or like planets like this, out in around other stars too, and those are what we call exoplanets. Though we've not really found ones quite so like exact to the ones in our own solar system. So what is an exoplanet? You might also hear them called extrasolar planets. That just means planets extrasolar outside of the solar system. Any planet that orbits a star outside the solar system. And loosely, we are defining them as masses that are about less than 13 times the mass of Jupiter. And this is roughly the deuterium fusion limit. So things that are larger than this are called brown dwarfs, which you may have heard of before, which are sometimes called failed stars. They're a little undermassive to be able to fuse hydrogen and be classified as stars, but they're a little too massive to be considered planetary bodies. So these are some loose definitions for what an exoplanet is. A lot of times in the literature for doing science, you'll kind of hear things called planetary mass objects. People aren't quite sure what to call them. We're looking for things, little things around stars, generally. Yeah, there is an immense diversity of exoplanets that have been discovered so far. I noticed that people aren't really talking much in the chat, but if anyone knows of any weird planetary worlds, shout them out. Have you heard of anything cool in the news? Not one person? Someone know, please. That's okay.
Like we have 55 Cancri.
55 Cancri is pretty cool. That's one. Yeah, I feel like in like the popular science like news, they talk about like lava worlds or puffy planets, things that are like evaporating because they're getting really blasted by solar radiation, or they're really low density because they have really extended atmospheres. There's things that are like called rogue planets that are actually not orbiting stars that kind of found floating on their own. Maybe they were kicked out of their planetary systems due to orbital interactions or other formation peculiarities. There's sometimes people are saying, oh, this planet's raining glass or diamonds or things, because different types of conditions on the different atmospheres can cause different kinds of materials to form. So yeah, there's a lot of different things out there. Generally, we classify exoplanets into a few like classes, the smallest being terrestrial, which are kind of roughly Earth size or up to like twice the size of Earth or smaller, mostly made of rock and metal. Some could possess oceans or atmospheres. A lot of times when people are thinking about habitability, they're looking to Earth-sized planets, because that's where we know that life exists on our own, in our own solar system. And then Neptune-like are similar to Neptune. Jupiter or gas giants are similar to Jupiter or larger, and super Earths are kind of twice the size of Earth. But yeah, they're roughly kind of split up into size classes and whether or not they have extended atmospheres. And the ways that we detect them kind of varies based on those different characteristics, because the detectability of those different types of planets changes depending on their own characteristics, I guess. So there are many ways to identify exoplanets, both directly and indirectly. Most of them are indirect. So a lot of times we're looking at data from stars. We're looking at a star's data and then finding some kind of blips or changes in that data that would signify that a planet's there. Kind of the main ones, kind of an overview of all the different methods that I'll kind of expand on as we go on, are transit photometry, and within that some transit timing variations, radial velocity, microlensing, astrometry, and direct imaging. And again, I'll expand on this a bit more. But yeah, a lot of different methods. So since exoplanets were first being discovered back in the 90s, we've had a huge uptick in the amount of detections starting kind of in the 2010s. So you can notice with the rise of radial velocity and transit method techniques, especially transiting surveys going online, space-based surveys such as Kepler and TESS, which are space-based telescopes that are surveying the sky, looking at stars, measuring their brightness over time. So that's the transiting method, that's the transiting method. So the transit method is where we're measuring a star's brightness over time. And what this is called a light curve. So just brightness on the y-axis, time on the x-axis. So we look for periodic dips in the brightness over time, indicating something, probably a planet, is blocking some of the light from the star. So the light, if you can think of it, 100% of the light of the star should be pretty constant. And then as something passes in front of it like that, there's a little dip that happens, and then it goes back to normal. And then every time it passes in front of the star like that, it'll have that same characteristic dip. So as we can see in this previous plot, this histogram, this is, oops, what happened? Oh my gosh. I don't know what happened, my bad. This is by far one of the most popular exoplanet detection methods. We do a lot of different follow-up observations to confirm transiting planet candidates, because a lot of them are still kind of unconfirmed. But we get a lot of kind of the first step of looking for an exoplanet from these transit surveys. And this is again another diagram of what that looks like, kind of an animation of planet passing in front of the star, blocking out some of its light, and then going back to normal. If we get very high resolution light curves, we can even see variations in the planet's own brightness over time. Because if you can think about it kind of like moon phases, we can see some of the part of the planet that's illuminated by the star when it's in our line of sight, when it's closer to eclipse. And then when it's in front of the star, when it's occulting the star, and we'll see its night side where it's not illuminated. And seeing those brightness variations, the day-night contrast also gives us a lot of information about the planet as well. So based on that and this animation here, what characteristics do you think we can measure with the transit method about the planet? Someone shout it out or say it in the chat. I actually can't see the chat. Oh wait, am I getting questions? I haven't been looking.
Yeah, there are questions. I've been helping you to answer them, but we can save all the questions to the end. Looks like
Okay.
someone shouted out the answer. Size, radius. And
Yep,
then-
radius of the planet, right? Yeah. So depending on the size and I guess the orbital speed as well, and then the path that it takes across the star. So if it's kind of more on like the edge of the disk of the star versus like straight like across like the center latitude of the star, the shape of that characteristic dip will be different, and then fitting that shape is how we determine the characteristics of the planet. All right. Oh shit. Okay, yeah, we can get to questions later. Should I just save them for later? Sorry, I just noticed the chat.
Yeah,
I wasn't
let's
looking.
save
Okay.
them for later.
Sounds good. All right, so within that, there's something called transit timing variations. So as I said, there's a periodic dimming in the brightness, the transit that happens when a planet passes in front of the star. Something that can happen for a planetary system with multiple planets in the system is that there's a third body in the mix that's perturbing the orbit of the planet that we see that's transiting. So it's possible that that planet is not a transiting planet that we can see in this type of signal, but it's causing some kind of orbital change. And that is causing like a offset in the transit timing. As you can see here, it's kind of like if this is like a zero point in the transit time, they're a little bit offset. So when we observe something like this, we can try to infer that there's like a third body present perturbing the orbit of this transiting planet that we know of, and try to see if there's another one hanging out there. And this is not as common of a way of identifying planets, but it is one thing that we check for when we look at transiting planets as well. Okay, moving on. This is the Doppler method, or sometimes called the wobble method, radial velocity method. So RV, radial velocity method, is also one of the most popular detection methods. So this is when we detect subtle shifts in a star's spectrum over time, indicating the star is wobbling. So if you guys know a little bit about the Doppler shift effect, for example, when an ambulance is coming towards you, the sound sounds a little bit higher pitched because those sound waves are getting kind of like compressed. And then when it's going away from you, the sound sounds a little bit deeper because the sound waves get a little decompressed. Same thing happens with light. So when a star is in orbit with a planet, it is slightly orbiting a center of mass. This is not very drawn to scale, but there's a planet here orbiting a star. And the star is also orbiting the center of the mass of the system. So it's also on a slight circular orbit. So when it's moving toward us, it's like it's slightly compressed. This is called blue shift, slightly compressed to shorter wavelengths. When it's moving away from us, going kind of back in its orbit, it gets a little bit decompressed or red shifted. It gets a little bit moved to longer wavelengths. And this will happen periodically as well, back and forth in an orbit. And when we observe this, we can try to infer that there's some second body in the system that's causing that to happen. So often these, instead of space-based telescopes, although there are some surveys that can do, some space-based telescopes that can do radial velocity spectra, a lot of times we're taking these radial velocity spectra from ground-based telescopes around the world. So here's another kind of GIF that illustrates that. So again, this kind of two-body system, the center of mass is this plus here. The star is orbiting around the center of mass. This spectrum is, as it moves to the right, that is called red shift when it goes to longer wavelengths. When it moves to shorter wavelengths, blue shift. And then it'll produce this kind of characteristic sinusoidal variation as it moves toward and away from us in our line of sight. So this is based on like a gravitational effect, and has to do with like the mass ratio of the planet and the star, as well as the distance between them. So based on that, I'll just kind of give it away, but this is how we measure planet masses. It is a little bit degenerate with knowing like the orbit of the system. We have to know the inclination of the orbital system to know for sure what the mass of the planet is. So often we say m sin I if we don't know the inclination of the system. But still unclear on the radial velocity and Doppler effect connection. Okay. So do you wanna elaborate on that a bit?
Well, we can save it for later. We can show it again.
Save it for later. Okay.
Yeah.
All right, I think I'll move on because I don't, how much time do I have?
Plenty.
Oh, plenty.
We have until the next hour.
Okay. Well, let's see. Can I expand on this a bit more then? The Doppler effect has to deal with yeah, the lengthening and compressing of waves, I guess. And that is what happens with radial velocity. So when we're measuring radial velocity, we're measuring the shift in the spectrum that, so like from a rest wavelength here, these like dotted lines, however much this offset is corresponds to a radial velocity measurement. Like, does that make sense? Because of like the shifting of like the compression of the waves, like the light. Maybe. Okay. Maybe we can discuss a little bit. Okay, let's see. Let's move on. There's also direct imaging. So this is one of the direct methods to detect exoplanets. The last two, the most common, were indirect methods. So planets that are sufficiently bright can be directly imaged, so we can see them actually in pictures that we take. This is done with very high-tech optics. So like Josh was saying, he works with extreme adaptive optics, stuff like that, coronagraphs to block out a star's light. And then when we can suppress most of the star's central light, we can try to see the planets illuminated around it. And there are only a handful of directly imaged planets and multi-planet systems out there. It's pretty hard to do because stars are bright and planets aren't. But they're working on a lot of new technology that'll make this a lot easier to do. But this is generally better for very bright, very large planets that are kind of further away from their host stars. Last kind of major one I'll go over is microlensing. So exoplanets can be detected by gravitational microlensing. So gravitational lensing is an effect that occurs when a sufficiently large body is between a source and an observer, and that distorts kind of the space-time in between the source and the observer into a lens. It's a little bit abstract, I know, but think of if this is like a massive star kind of further away from us, this is a red star in front between us and this massive star. When this foreground star is in front of it, the light around the light of the background star can kind of curve around the foreground star, like warp around it, and it gets magnified kind of like a lens does. And if there's a planet orbiting that foreground star, there can be an additional lensing effect that occurs from the planet passing in front. And this isn't a super common detection method, but it has been done. And it has like a characteristic duration. So people can identify like, oh yeah, this is when a planet was passing in front, there was this extra. Yeah, this part is relevant to rogue planet stuff. Yeah, exactly. All right. I thought I had an additional plot somewhere in here, but I'm missing it. So I think I'll move on. So what do we do once we find exoplanets? What can we find out from them? Why are we interested in finding more? A lot of times we are looking to find exoplanets to answer questions about like how exoplanets form, provide some context for how our own solar system formed and how life came to be and things like that. So yeah, studying and discovering new types of planets helps to inform theorists about theories about trying to determine how planets form. Can continue the search for extraterrestrial life, exobiology, exobiologists looking to find other signatures of life on different haplotype planets out there. So let's start with a little bit of background on protoplanetary disk, the birthplace of planets, planet formation stuff. So when a star forms, It's a kind of a big collapse of gas and dust that kind of collapses down due to gravity, starts rotating. The central star creates a bunch of material, and then anything that's not accreted kind of flattens out into a disk around it. And then that disk of gas and dust is where planets are formed. And we're not super sure exactly all the processes that occur to create the different types of planets we see. As we discussed earlier, there are lots of different planets out there, ones that are similar to the ones in our solar system, but also lots of ones that are very different. So finding a lot of different exoplanets helps us to kind of make sense of what types of planets are common, what kinds of processes need to occur to explain the existence of such planets, what kind of planets can exist together in the same systems, what kind of stars can host those planets, and things like that. For example, different types of core formation and accretion scenarios for like rocky cores to retain very large gaseous atmospheres like a gas giant. Someone's not muted, by the
I
way.
fixed that. Don't worry.
Oh, okay. And then something more like the Earth, where it's mostly just like a rocky core with not much atmosphere. We also study planetary interiors, also to inform kind of planet formation, as well as just different planetary conditions out there. Studying different the interiors of the planets, the core and mantle ratios, also the surface conditions, what's going on in the outermost layer of the planet and what the atmosphere is like. On the surface, we are just beginning to be able to study atmospheres with the new James Webb Space Telescope, if you guys have heard of that. Although we can do that with other spectrographs as well on ground in space. The James Webb Space Telescope has really been revolutionizing our ability to be studying planetary atmospheres, especially on smaller rocky bodies. We're able to see how hot it is on the surface of a planet, how it changes from day to night, the effects of the stars' irradiation on the surface of the planet, the mineralogy and geology, and also what the implications of those things are on possible habitability. For example, this is a spectrum from James Webb, I believe a real spectrum, and along with a model of, actually I don't remember what planet this would be. Oh yeah, this is a WASP 96. So this is a hot Jupiter planet. So a planet just like Jupiter, a gas giant that's very close to its host star, and detections of water. It's very high resolution for something like this kind of work. Yeah, we're pushing our limits these days, able to see more and more detail about these different types of planets, and yeah, I think that's all I have to say about that. So yeah, I think that's pretty much it. We can recap and discuss, because I know there were a lot of questions as I was going, so I might have like glossed over a lot. But yeah, I think I want people to have kind of these main takeaways. What are the most common methods of planet detection? Someone shout it out. Radial velocity in transit for sure, yeah. Microlensing is pretty uncommon, actually. And Faye's we're gonna do Exoplanet Archive together, so Faye will show you some plots of what exoplanets have been discovered, and you can see the distribution of different things that have been discovered by different methods, which would be interesting.
Yeah.
What do we measure with the transit method? Well, I guess we already said that earlier. Radius. What do we measure with RV? A planet property. Yeah. What do you think we'd measure from direct imaging? I don't think I said it, but you guys can guess. Think about it. There's not one right answer. Oh yeah, for sure. Yeah, you can measure the star planet distance pretty well in an image. Not so much that's not really like a measurable property, but definitely it helps inform planet formation stuff. Not the shift, no. I think can you get temperature from imaging?
Yes, if
Yeah,
you spread them out
yeah,
into spectrum, you can do it.
right. Yeah. I was thinking like, yeah, from a very like from a good image, you can get this like the size of the planet too. And if you can map out the orbit pretty well, you can get the mass as well. But you can also get those from the other methods. And I guess I kind of gloss over this too, but what do we learn from different types of exoplanets? I guess different formation histories, right? Different from gas giants, we can kind of learn more about, how atmosphere is accreted in the outer solar system, in the outer regions of the planet forming disk. From rockier planets, more about habitability, about core formation. And then where does the data come from? I know I kind of glossed over that too. Yeah, a lot of it comes from space telescopes, especially photometry. So the brightness over time measures. That's easy to survey from the sky. It's just like kind of taking little like sweeping pics of the sky all the time. Good. We also use a lot of ground-based telescopes, spectrographs, to get spectra to measure the radial velocities of planets. We also need ground-based telescopes for direct imaging as well. A 10 centimeter amateur telescope, yeah, whatever you got, you can use. We use those kinds here too for looking taking around island and looking for things. Is there a way to measure the temperature of the planet without direct imaging? And if so, how? I think usually the way it's wait, Faye, are you answering?
You should. This is your research.
Yeah. Typically I think most people estimate it from the temperature of the star and how far it is from the star. And it's kind of just like a relation based on that, how far it is from the central star, and like the radiation that it can receive based on the distance. Show gas, ice, which one is more important to discover? Makes you say for ice versus gas type planets. I don't think there's any one type of planet that's more important to discover. I think definitely, and when we go over to Exoplanet Archive too, we'll see that there's still a lot of parameter space to fill out on the different types of planets that we want to see. I study little planets, Earth-sized planets that are really close to their host stars. I think that really makes me say wow, because they're really small. it's kind of like the leading edge of what we're able to detect with the current technology. So that's really kind of incredible what we're able to do these days. Yeah, so yeah, that's correct. Sorry. So someone said if the planet has an atmosphere, the distance from the star would not be like an accurate indication of the temperature, for example, Venus. And yeah, that's correct. So there's like an equilibrium temperature and then like an effective temperature of a planet. And the atmosphere of will largely change that. Especially for Venus. So yeah, unfortunately, like if you don't have like a good spectrum or like a direct measurement of the planet, it is hard to infer the temperature. But usually if you don't have those direct measurements, that's just like kind of the inference you make is from just like the distance relation. Why is the triangle still curved while the planet is completely shouldn't be trapezoid shaped? Why is the transit light curve still curved while the planet is completely in front of the star? Shouldn't it be a trapezoid shape? Oh, like why isn't it like completely flat at the bottom? Oh, did someone answer that? Oh, wait, no, it's a new question. So actually,
You want to take that?
yeah, let me go back to I think this part. It's kind of more or less flat, but like the edges here, I guess, kind of curve, and it's depending on like the different the different kind of planet stuff. Like some can look flatter than others, but it's curved here because the star's brightness over the star's disk is also not constant. So the edges of the star, when you're looking at it, will have something called limb darkening, the very edges of it, because when you're looking through a star or looking at a star, you're actually looking through layers of gas as well. So you can imagine if you're looking at at a sphere gas, that looking at the edges of it, it'll be kind of like thicker than looking at like the face of it, if that makes sense. I don't know if that makes sense. But so when a planet blocks the edge of a star, like the proportional amount of light that less than the body of the star, and as it like crosses over the star, it's like this like gentle slope that happens because of like the limb darkening on the edges of the star. Does that make sense? Okay.
Yeah, the keyword is
Which temperature?
you can
Sorry, what?
saying the keyword is limb darkening. You can Google about the star.
Oh yeah, I can Google limb darkening for further detail. Yeah, if that was a little unclear. Effective and equilibrium temperature. Okay, thank you for answering that, Faye. Limb darkening. Okay. Great questions, everyone. Anything else?
Well, maybe we should move on in the interest of time. Thanks a lot, Rita. Thanks a lot for
Yeah.
the interactive presentation. Appreciate that.
Oh yeah, shoot. I
Oh,
took
don't
more
worry.
time than I thought I did.
We can go over a bit.
That went by fast. All right.
Okay. All right. So the last topic for today, can everybody see my screen?
Yes.
Okay, good. So the last topic for today is the so-called NASA Exoplanet Archive. And well, Rena has just shown you the various exoplanet detection method. Now let's take a look at the real planets that are found by these various techniques. So the NASA Exoplanet Archive is actually an online database maintained by NASA and contains the useful information on individual planetary system as well as on the whole population of known exoplanets. Yeah, this is a database, but the facade is just a website. And let's walk through some of the key features. So you can see the website reports the latest number of confirmed planets. That's 5,678. And that was updated, I think, 3 weeks ago, June 25th. And they also list some of the planets found by the latest NASA mission. For example, this one, the TESS mission. This is one of the most important missions that NASA is running as a transit mission, as Rena mentioned. And it also has planet candidates. By candidates, what we mean is that these are most likely planets, but we haven't confirmed them through, say, mass measurement. So, the current standard for confirming a planet is either you have measured the mass of the planet, or you have ruled out all possible false positive scenarios, including eclipsing binaries. And usually, these follow-up observation takes some resources. And people are hard at work confirming planets, but it is almost always the case that the number of candidates will outweigh the number of confirmed planets. And you can click on all of these, and it will take you to a table that lists the key parameters of the systems. For example, the planet name of the host star. Well, these are some bookkeeping things like the parameter sets, number of stars. Some stars can be binary or triple star systems, number of planets. You can see some planets, some systems have multiple planets. For example, this one has 2 planets. The discovery method, as Rena mentioned, whether it's transit, radial velocity, imaging, microlensing. Year of discovery facility, which is a telescope that we use to discover the planet, for example. Keck is a telescope in Hawaii that our team use a lot. And many of these are actually from space-based facilities like TESS and Kepler. We'll talk about TESS in more detail later in the course. And yeah, you can go through the table. It also provides the reference or the original paper that published these planets. The orbital parameter, semi-major axis, planet radius, planet mass, a lot of things. Okay, let's go back. So a key feature of the archive is that you can type in the name of your favorite system. So one of my favorite system is TY 1136. The reason why I'm interested in it, this is actually a system discovered by our group. There's 6 planets that you can see here. The host star is a sun-like star, almost exactly solar radius, 0.98 solar radius, and an effective temperature pretty close to sun too. But the planets are quite different from our solar system planets. So by the way, planets are named with lowercase letter from B onwards. So the planets are named B, C, D, E, F, G for the 6 planets. The reason I picked this system is that the system is very peculiar in the sense that all the planets are within the orbit of Mercury. For example, the longest period planet, it only has an orbital period of about 40 days. In contrast, our Mercury, which is our innermost planet, has an orbital period of 88 days, which means that all 6 planets are packed compactly within the orbit of Mercury. And what could have given rise to such a compact orbital architecture is still active research. So that hopefully gives you a glimpse of how to look up the information on individual system. So there's a reference here. If you click it, it will take you to the NASA ADS system that we talk about in week 1, and you can check out the paper. Okay, so coming back to NASA Exoplanet Archive, another useful feature is that it periodically reports the latest news in exoplanets. For example, This page is reporting Gliese 12b and Specular 3b, which are two Earth-sized planets nearby, and they are very favorable for follow-up observation. Another key feature is that Exoplanet Archive also produce these so-called pre-generated plots. So let's maybe look at some of them. So the most commonly used one is this one. This shows the mass of the detected planet versus the orbital period. And the different symbols represent the different detection methods. For example, radial velocity, transit, microlensing, imaging, transit time duration. Some of these we have talked about. So the key thing you can see is that the various detection methods tend to discover planets in different part of the parameter space. For example, the transit method tend to detect the shorter period planets, those with orbital period less than 100 days or so. Whereas the radial velocity method, which again is measuring the mass of the planet, these tend to discover planets that are more massive, typically at least 20% or 30% of Jupiter mass. Yeah, so this table is almost updated daily. So you can see this was generated in July 15. Okay, so let's go back to the pre-generated plots. So there are a whole bunch of other related plots, for example, period versus planet radius, the year of discovery. You can see there are 2 years that are particularly prolific in terms of number detection. This is 2014 and 2016. And I think both of these correspond to a large data release from the NASA Kepler mission, which is a workhorse for the transit detection about a decade ago. Okay, so the other plots, we'll go into making some of these plots shortly, but just want to alert you, you can directly borrow these plots. All right, so coming back to the NASA Exoplanet Archive. So in this part of the website, you can look at the various planets discovered by the different missions. So I mentioned TESS, which is ongoing NASA mission. Kepler is kind of the predecessor for TESS. And K2 is the extension of the Kepler mission. KELT is a ground-based mission. Similarly, Euclid is also a ground-based mission. And there are other useful tools. So I won't go into detail of these today, but if you ever end up working in exoplanet research, some of these tools are very useful. Okay, so I think that was a quick overview. Let's take a look at the Python notebook that accompany the Exoplanet Archive. So let's make use of the various knowledge we have picked up in the first 3 weeks. So let's first import some of the useful package. OS is a system for handling, directory saving files. Pandas, we have examined this package. This is for handling a large table of data. NumPy, this is usually for handling data and quick mathematical operation. And Joshua has just covered Matplotlib, which is used for making plots. And this is a sub-function in Matplotlib, so-called inline. This is allowing the plots to appear between the different Python or the Jupiter cells. This is very handy for displaying the plots in time. Okay, so let's make use of the data from NASA Exoplanet Archive and make a mass radius diagram, where the horizontal axis is the mass of the planet and the y-axis is the radius. So this cell basically tells the code where our saved data is located. It's in a folder called data, and the file name is called confirmexample.csv, where CSV stands for comma separated values, a commonly used format for storing data. And we use Panda to read the data, which is simply in this function read CSV. And all you need is to provide the path to the file and a comment. This is removing the header of the file. And now we are displaying the first 5 entries of the table. You can see, again, this is what we saw earlier, the planet name, the host name, the discovery method, the orbital periods, etc. So a useful tool in Pandas is that you can tell Panda to display the shape of your data. This is basically this is basically done by dot shape, and you can see we have 762 entries, and each entry will have 72 columns of different values. Okay, to make a mass radius diagram, we have to know that mass and radius are respectively named PL_B mass. J stands for Jupiter. So the mass and radius are known units of Jupiter, and we can easily use the function that Joshua has just shown us, which is plt.plot. And this is exactly what we mean by mass radius diagram. You can see that here the data is not very clear. Some of the data are really clumped together. One way you can clear up the data, the plot, is by using a log scale, which is simply by calling the keyword xScale and specify it as log. Now, all that 762 planets are shown here, and you can see they span somewhere between 0.1 Jupiter radius to about 2 Jupiter radius. And the mass spans 1,000 of Jupiter, which is closer to Earth. Earth is about 3.3% of Jupiter mass, all the way up to about 10 Jupiter mass. Note again, 13 Jupiter mass is the upper limit. Anything larger than that will be classified as a brown dwarf rather than an exoplanet. Okay, so let's look at another example plot, which is visualizing the radius distribution of all the transiting planets. So I have pre-downloaded data, but you can do the same by going back to the NASA Exoplanet Archive. Again, reading the data using pandas and displaying the first few headers of the table. And now we are making a histogram rather than a scattered plot of the radius. And again, you can see most planets have a radius below 10 Earth mass, 10 Earth radius, which is right about Jupiter radius. And we can also make the histogram more clear if we do it, or if we bin things in a log space. Okay, so the assignment for this part of the workshop is for you to make orbital period versus radius diagram for all the transiting Kepler planets. And this can, again, be downloaded from the NASA Exoplanet Archive. Let me just quickly show you how to download the data. So if you go to the table here, there's an option to download data, and you want to select CSV. This is usually the easiest to manipulate. And you can specify to download all the columns or currently selected columns. And you click this button, download table. It will be saved on your local machine. Usually the website is pretty quick. Okay, so the final part of the assignment is to make a plot of whatever 2 parameters you want. Pick and choose and see if you can discover something using the known exoplanetary population. Okay, that's all. Let us know if you have any questions. Well, I haven't been monitoring the chat. Is there any question already? So Akriti asked, does the NASA archive have already discovered planets? Yes, all of these are discovered planets. If you want to discover something new, you have to use the raw data from, say, for example, tests. And we will show you how to do that later in the workshop. Okay, looks like Rena already answered a few questions. All right, folks, any other questions before we end? Yeah, so one thing I forgot to mention is that NASA, or for example, Harvard or Cornell, some of the big organizations, they help to contribute to community by maintaining these online database. NASA Exoplanet Archive is one example. Later, we will see other example, for example, the TESS database, the Gaia database. So as a researcher, you will learn how to access the data on various databases. And the demonstration we had so far was one of the ways where you can use the database. Another way is to write an API or directly using the code interface to access those data. And those tend to be faster. We will show you how to do that later.
Register now on bit.ly/Intro2Astro 2024.